Today we're going to learn about variation of wave function and probability densities of a particle in 1D potential well of infinite wall height when n is equal to 1, 2, and 3. In quantum mechanics, the wave function and probability density of a particle in a one-dimensional infinite potential well can be described using the Schrödinger's equation and the corresponding solution. The infinite potential well consists of a particle confined within a region between two infinitely high potential walls. The solution to the equation results in quantized energy levels and corresponding wave functions for different quantum states. Particle inside a potential well of infinite height. Let us consider a particle of mass m inside a potential well of width a, moving along x direction. The potential inside the box can be considered as 0, and the outside the wall potential is infinite. Inside the well, v is equal to 0. The wave equation can be written as d square psi divided by dx square plus 8 pi square m divided by h square into e into psi is equal to 0. This is the equation 1. The equation 1 can also be written as minus h square divided by 8 pi square m into d square psi divided by dx square is equal to e into psi. Then h into psi is equal to e into psi. Let 8 pi square m divided by h square e is equal to k square. Let this equation be 2. Thus equation 1 can be written as d square phi divided by dx square plus k square psi is equal to 0. This is equation 3. The general solution of the above equation can be written as psi is equal to c into cos k into x plus d into sine k into x. This is equation 4. Applying the boundary condition to the equation 4, using these boundary conditions in the solution of the wave function can be written as first condition is at x is equal to 0, psi is equal to 0. That is 0 is equal to c into cos 0 plus d into sine 0. Then c is equal to 0. Therefore, phi is equal to d into sine into k into x. This is equation 5. The second condition is at x is equal to a, psi is equal to 0. That is 0 is equal to d into sine ka. Since c is equal to 0 or d sine ka is equal to 0, therefore psi is equal to d into sine into n into pi divided by a whole into x. This is equation 6. Substituting the k value in equation 2, we get 8 pi square m divided by h square e is equal to n square into pi square divided by a square. E is equal to n square h square divided by 8 m into a square is the final equation. N is equal to E is equal to n square into h square divided by 8 ma square. N is equal to 1. When n is equal to 1, it represents ground state and the corresponding energy is called ground state energy or zero point energy. Ground state energy, the equation is given by E naught is equal to h square divided by 8 into m into a square. When n is equal to 2, it represents first excited state. And the first excited state energy E1 is equal to 4 into h square divided by 8 into m into a square, which is equal to 4 into E naught. When n is equal to 3, it represents second excited state, and the second excited state energy E2 is equal to 9 into h square divided by 8 m into a square, which is nothing but n into E naught. Now let's see eigenfunctions, probability densities, and energy eigenvalues. The energy eigenvalue of a particle in a potential well of infinite height is given as E is equal to n square into h square divided by 8 into m into a square. The eigenfunction is given by psi subscript n is equal to whole root 2 divided by a into sine into n into pi divided by a into x. The probability of location and energy values varies in various allowed energy levels as given below. When n is equal to 1, it is in the lowest energy state and it is termed as ground state, and the corresponding energy is called as 0-point energy and given as E naught is equal to h square divided by 8 ma square. The eigenfunction for ground state is psi is equal to whole root 2 divided by a into sine pi divided by a into x. Wave function psi is equal to 0 at x is equal to 0 and x is equal to a, and maximum at x is equal to a divided by 2. When n is equal to 2, it is the first excited state and the energy in the state is given as E is equal to 1. The eigenfunction for the first excited state is psi is equal to root 2 by a into sine 2 pi by a into x. Wave function phi is equal to 0 at x is equal to 0 and x is equal to a, and x is equal to a divided by 2 and maximum at x is equal to a divided by 4 and x is equal to 3 a divided by 2. The probability density of phi is maximum at x is equal to a by 4 and 3a by 4 and 0 at the walls. That is x is equal to 0 and x is equal to a, and at a by 2 as shown in the figure.